For the last session, before the poster session and after this. We have first Federico Holik, who's going to talk to us about the interpretation of probabilities and generalized probabilistic models.
I work at the Institute of Physics of La Plata. This work is made with other collaborators of our group and is funded by CONICET and Chantal Foundation. So the debate regarding the interpretation of probability remains still open in the literature. These interpretational problems become particularly important when the probabilities arising in quantum phenomena are considered. For example, this is expressed in a quotation by Feynman, who says, "I should say that in spite of the implication of the title of this talk, the concept of probability is not altered in quantum mechanics. When I say the probability of a certain outcome of an experiment is P, I mean the conventional thing. That is, if the experiment one expects that the fraction of those which give the outcome in question is roughly P. I will not be able at all concerned with analyzing or defining this concept in more detail, for no departure of the concept used in classical statistics is required." So this is surprising, but he finishes the argument saying what is changed, and changed radically, is the method of calculating probabilities. So even Feynman concludes that there's something new, something radical going on here. The sum rule of probability amplitudes given rise to interference terms was rapidly recognized as a non-classical feature. Later, it was discovered that this was strongly related to the non-existence of Chern distributions for non-commuting observables. So, the question that I want to pose here is a debate, is given that there are relevant physical theories which suggest a radical departure from classical probability theory, there's a need here for an interpretation, at least for an interpretational debate. And this debate should be given in both sides of the problem. The conceptual side, so what is ontologically going on here, or conceptually, how can we interpret probabilities? And at the same time, on the technical side, which are the best mathematical grounds in which we can formulate or found probability theory. So this is my talk will be about this, trying to define some problems, trying to define some outlines of the solution. So one of the most important axiomatizations in probability theory is due to Kolmogorov. In his approach, probabilities are considered as measures defined over a Boolean sigma algebra of a sample space. Interestingly enough, states of classical statistical theories can be described using Kolmogorov's actions because they define measures over the sigma algebra of measurable subsets of phase space. An important example of a classical probabilistic model is provided by the point particle moving in spacetime, whose states are described as probability functions over a six-dimensional space. So suppose that A represents an observable quantity, such as the energy or angular momentum. So it is defined as a function over space. Then the proposition, the value of the observable A lies in interval delta, defines a testable proposition which we denote by A delta. It is natural to associate to A delta, which can be represented as so it is very natural to associate to this proposition a subset of phase space, because they are given in a 1-1 correspondence. So if we do this, the probability of this proposition, given that the system is in a probabilistic state mu, will be given by the measure of this subset of phase space. In this way, there is a correspondence between a classical probabilistic state and actions of classical probability theory. Why? Because classical probabilistic states are measures over a sigma algebra of subsets. In this case, subsets of phase space. These are a set of actions which are equivalent to the Kolmogorov actions. So as you see, you have a function which goes from a sigma algebra to 0, 1 and satisfies these conditions. So a state of a classical probabilistic theory will be defined as a Kolmogorovian measure with the sigma algebra equal to measurable subsets of phase space. But quantum mechanics shows us models of systems which depart from the Kolmogorovian setting. I'm going to try to clarify in which sense they depart. So, an interesting approach to the statistical character of quantum systems consists in considering quantum states as measures over the non-Boolean structure of projector operators in a Hilbert space. As is well known, projection operators can be used to describe elementary experiments. So this approach allows for a comparison between quantum states and classical probabilistic states. Virchow and von Neumann showed that the empirical propositions associated to a classical system can be naturally organized as a Boolean algebra. This Boolean algebra is just the sigma algebra formed by the subsets of phase space. While classical observables are defined as functions over phase space and form a commutative algebra, quantum observables are represented by self-adjoint operators which fail to be commutative. Due to this fact, empirical propositions associated to quantum systems are represented by projection operators which are in one-to-one correspondence to closed subspaces related to the projective geometry of a Hilbert space. It can be shown that empirical propositions associated to quantum systems can be endowed of a non-distributive lattice structure, which is shown to be, because of non-distributivity, non-Boolean. So, states of quantum models can be described in a way which is analogous to the classical case, but using operators acting on Hilbert spaces instead of functions over phase space. Suppose that we want to represent a proposition in a quantum experiment, such as the value of an observable A lies in the interval A. So this will be represented mathematically by a projection operator acting on a Hilbert space. This is strongly connected with the spectral decomposition theorem. The probability assigned to the event, to this event, the value of the will be given by Born's rule. So essentially, what we have here is a kind of measure theory in a non-commutative algebra. So Born's rule defines a measure on the projection lattice with which it is possible to compute all probabilities and mean values for all physical observables of interest. This can be put in an axiomatic form which resembles the actions of Kolmogorov. Due to Glisson's theorem, a quantum state can be defined by a measure S over the orthomodular lattice of projection operators as follows. So we have, instead of mu, we have a function which goes from the projection lattice to the interval 0, 1, satisfying a set of actions which are similar to those of Kolmogorov. But the main difference here is that this event algebra representing empirical proposition, has a very different structure to that of the Boolean algebra. So there will be a great difference between quantum probabilities arising in quantum states and probabilities arising in classical systems. Notice that for the classical state, we have a correspondence between states and actions of Kolmogorov. But now, a quantum state will be not equivalent to a Kolmogorovian probability anymore. But there is some resemblance of that. So, in a series of papers, Murray and von Neumann search for algebras more general than the bounded operators of a Hilbert space, for reasons that I'm not going to explain here because of time. But these new algebras are known today as von Neumann algebras, and their elementary components can be classified as type 1, type 2, and type 3 factors. Further research showed that there exist theories of interest, such as algebraic quantum field theory or algebraic quantum statistical mechanics, in which more general factors than those appearing in standard quantum mechanics are needed. So, if we come back to these actions, this lattice could be Boolean, could be the orthomodular lattice of the Hilbert space, or it could be a more general orthomodular lattice. So we have different models of theories, of relevant theories in physics, which have essentially different probability theories from at least from the mathematical point of view.
May I just, because if it is not denumerable and there was also actually, if it is not denumerable, how do you write that same analogy for non-denumerable?
Typically, that is a very important question, because when von Neumann tried to figure out all this mathematical formalism, he wanted a measure theory. This is not like a tricky thing, or no. He wanted something which gives you conversion things, like if you want to compute a probability, or if you want to compute a mean value, you need an integration theory in an operator algebra. So in order to have that kind of thing, you need an analogous of the elements of a Boolean algebra and a condition of sigma additivity. This is essential for conversions questions. So it plays the same role, not the same, but a similar role to that role played in Kolmogorov's theory.
So you have an analog, I'm just trying to inform myself. You have an analog of Lebesgue integration in this quantum domain, right?
It's more like a still shift, but okay, yes, you have an integration theory. Yes.
Okay.
Yes. So this allows you to extend a quantum-like theory to the infinite dimensional case of the Hilbert space in a consistent way, and at the same time to propose a generalized formal setting, which could be nowadays called that of von Neumann algebras or that of C-star algebras. But let me show you something which I think that is very important with some examples. It is very important to mention that the connection with classical probabilities is not lost at all, and it is done in a very symmetric way. An arbitrary orthomodular lattice can be written as a sum, like a kind of direct union of Boolean algebras, of maximal Boolean algebras. If you have a non-Boolean algebra, or if you have a non-Boolean lattice, there are Boolean subalgebras. And the lattice can be put as a kind of direct union of all these Boolean subalgebras. This has a very clear physical and operational interpretation, which is, if you have a quantum system, you have contexts. If you have an experiment, a particular setup on the lab, this is a table in quantum optics, if I put a particular setup, then it will be represented by a Boolean subalgebra, which is maximal. And if I make another experiment, there will be another Boolean. So all possible Boolean subalgebras are susceptible of representing concrete physical experiments, and the state of the system, represented by a density matrix, when restricted to a Boolean subalgebra, will define a Kolmogorovian measure. So the connection with classical probability is not lost, but the quantum state, which is no longer completely equivalent to a classical probabilistic distribution, is equivalent locally with respect to any particular experiment. But the state of the system is a pasting together in a quotient way of these Boolean subalgebras. So, well, I will just put some example. This is a Boolean algebra of two elements. So this will be a coin, face or up or down, and then a classical state will be a measure here. And then the state of a coin, which will be a classical bit, it will be a segment, because each state, for example, the segment in the center will be probability 1/2, 1/2. The segment, the point on the extreme will be probability 1 and 0, and so on. So the state of a classical coin will be like this. It will be a convex set, and a measure here. By a quantum, for example, if we take a qubit, then we will have 0, 1, and one direction and its orthogonal complement. So there will be one Boolean subalgebra here, and the quantum state will define a measure here. But if we jump into another Boolean subalgebra, another direction, so we have a family of coins in every direction of space, pasted together. harmonically by the quantum state. But this state, from the geometrical point of view, the set of possible measures will define a sphere, no longer a strip. The classical qubit is a strip, the quantum qubit is a sphere. So geometrically are very different. So you can do the same for three-dimensional systems and so on, right? So this will be a skeleton of a three-dimensional quantum logic. So, as a conclusion, a quantum state will define a Kolmogorovian probability on each maximal subalgebra. Something completely analogous occurs for more general physical theories of importance. But these Kolmogorov measures are pasted in a coherent way. Born's rule makes the work. And this can be, of course, extended to a more general setting, as I said before. So you replace this L could be a Boolean algebra, a type 1, the lattice of a type 1, type 2, or type 3 factor, and more general theories could be conceived according to this setting. So there is a very clear sense in which we have, at least from the formal point of view, a generalized probabilistic theory. So this is well behaved from the mathematical point of view. And of course, then it comes the question about how to interpret this non-distributivity or non-Booleanity of the empirical propositions. So another more general setting is to consider a set of states of a particular probabilistic model just as a convex set. This approach would be more general to that represented by orthomodular lattices. And then in this setting, while classical systems can be represented as simplexes, non-classical theories will display a more involved geometrical structure. As I told you before, a qubit, a classical bit was just a line segment, and the qubit was a sphere. And for example, if we take, I will try to avoid technicalities, if you have a probabilistic system which has as a state space a triangle, then you consider the faces of this triangle and these points here. And then you can show that the faces form a lattice. And this lattice will be isomorphic to a Boolean algebra in the case that our system is classical. And the system will be classical if the convex set of states is a simplex. If we take a quantum state and consider all possible faces of the set of states, then we will find that the lattice of faces of the convex set is isomorphic to the orthomodular lattice of von Neumann. So there is a connection between the convex set approach and the lattice theoretical. But the convex set approach is much more general.
But what's then the union of two convex sets?
The union
It's not a convex.
is not convex. So you need to
But
take...
what is your operation you take? It's corresponding.
Well, it's a tricky thing. because-
Intersection is clear, that's convex again.
Yeah, it depends on the model. It depends on the model because, for example, if you have two quantum states, you need to first take a tensor product of algebras, and then there you define a convex set, right? But you could just take a kind of tensor product of convex sets. You just take the Cartesian product and then take the convex hull, and that will give you a new model, which maybe is not quantum theory. This convex sets approach is very general. So many models can be included, and some fantasy models as well, like, I don't know, Popescu, Rorley, boxes, and things like that, you see?
Okay.
So this fact that the faces of the convex set are isomorphic to an orthomodular lattice is a non-trivial fact. I mean,
Yes.
not all theories will. If you take an arbitrary convex set, you will not be able to define a good orthocomplementarity relation, always.
Yes.
It will be always a lattice. You can always show that if you give me a convex set, you will have a lattice of faces. But, so, these models can go far beyond classical and quantum mechanics. So the fact that the states of physical theories can be considered as measures over different sets of possible experimental results reveals an essential structural feature of all possible physical statistical theories. statistical model must specify the probabilities of actualization of all possible measurable quantities of the system involved. This is a feature which is common to all models, no matter how different they are. The study of the ontological constraints imposed by this general structure was not addressed previously in the literature. Well, this is not so true, as you will see later. But so in the end, the structure of these measurable properties will impose severe restriction on the interpretations of the probabilities. So I want to pose a question. How can we give an interpretation of probability theory, given that we know that there are more general models than those provided by Kolmogorov? And of course, this could be related to the fact that psychologists find different probabilistic models, just from the beginning. This is more inspired in physics, of course. That is why it has a lot of structure in it. But the question is more general. So, I will jump all this because it's the technical explanation that we can just, if someone is interested afterwards, we can discuss it. But this is like a, so, these are the, so, sorry. So, a question arises. Can we say something about the nature of probabilities by simply looking at the structural properties of the above described frameworks? Is it possible to find a theoretical framework which allows us to give an interpretation of probabilistic statistical models? So, this is problematic from the beginning because this generalized setting is a mathematical framework capable of accommodating models of a very different nature. But as we shall see, we can say some general things. Given that it contains classical, well, this is just a, so, but there are some specific features which allow us to extract some structural conclusions by studying the relationship between the lattice of properties and the geometry of the set of states. In order to find an answer to the above questions, let us start first with an example, an approach which was developed first by R.T. Cox, which says something like this. He says, if a rational agent deals with a Boolean algebra of assertions representing physical events, a plausibility calculus can be derived in such a way that the plausibility function yields a theory which is formally equivalent to that of Kolmogorov. So he says, I'm a rational agent. I use classical logic, so I want to decide which is the most convenient way in which I must assign probabilities. So he concludes that there is a strong relationship between the logic or the operational logic associated to the algebra of assertions and the forms of the actions of probability theory. What we did with a group of Argentina is to extend this result and say, well, what happens if we give up the metaphysical assumption that all possible event algebras are Boolean? Because in quantum mechanics we are faced with contextual phenomena. We have to accept as an empirical fact that phenomena is given in a contextual way. So a similar result holds if the rational agent deals with atomic orthomodular lattices. For the quantum case, non-Kolmogorov measures arise as the only ones compatible with the non-commutative character of quantum complementarity, or contextuality.
Can you quickly say what the plausibility function is like?
It's just equal to the, you can show that you derive the von Neumann actions of a measure, and then by Grissom theorem you get the
Is the plausibility function just an ordering, or is it qualitative? What is it?
No, it's a function from the lattice to the real numbers.
Okay.
You are assuming that, because you are just saying that you want to assign a degree of belief.
Oh, okay.
So it's kind of Bayesian approach, right?
And why the word rational there?
Rational. Well, because you need a definition of rationality. In order to get this, you need something which works. So you need.
Because it works. That's why.
Yeah, something that works,
Yeah.
and it's well, maybe it's not the best definition of rationality.
I don't think so.
No, but no, okay.
But
Okay.
it works. I agree.
It's a tricky thing, but
I agree with you.
But they're supposed to do a rationalization. So you need to account for everything. You say, I need a standard way to compute things. I need it. I need regularities. It must not be arbitrary. But at the same time, I must take into account
I understand.
phenomena. So phenomena is telling us that,
And you get a unique solution.
and you get a kind of unique solution. That's
Good, okay.
so yes, maybe rational is not the best. I should one. So
But Cox used the word rational anyway.
let's use the word rational. Yes.
Complaining about Cox.
Yes. We can blame him.
Yeah.
So Cox's approach works as follows. You start with the Boolean algebra, representing the domain of possible events available to a rational agent. I mean, a rational agent is someone who wants to do the things right. He wants to bet and he wants to win.
Oh, I think you have a problem with that.
Okay. I'm not saying it's the best definition of rationality, but so the algebra is assumed to be distributed because this fact reflects that the logic used by the agent is essentially classical. So there's a plausibility function, which is conditional, and then he goes on and derives conmode of actions. This works as a sort of inference calculus. When we have complete certainty, the agent uses classical logic in order to make deductions. When he has no certainty, he must use a degree of belief functions. And it turns out that if the function phi has to be compatible with the algebraic properties of the Boolean algebra, there are not too many options at hand. Phi has to satisfy up to rescaling a set of laws which are equivalent to those given by Kolmogorov actions. So, and the same extends for information measures. So if there's a natural definition of information measure, Cox suggests that, and other authors completed the work, and you can show that Shannon's information is a natural information measure for a Boolean algebra. Now then, of course, in another paper we showed that the von Neumann entropy arises as a natural measure of information, derived from the non-Boolean character. So you have classical, you will have the phase space, and the subsets of phase space, and Shannon's entropy. In the quantum case, you will have your comodular lattice of projections, and then you will have the von Neumann entropy. And if you go to a general case, you will find the measurement entropy, which is an entropic function which can be used for generalized probabilistic models. So you will have the model here, the complete theory, and then this theory suggests which is the operational logic, and you contrast this with experiment. And then you derive the structure of the actions of probability for each theory, and then you have the convex sets, which are the set of states defined on these theories. So these are some of our. This is a paper of Cox, and this is a paper in which the Shannon's entropy is derived, and this is one of our papers, and showing that the Cox approach can be extended to the non-Boolean case, and in this way we study von Neumann entropy and more general entropic measures. So the existence of this approach opens an interesting perspective for a Bayesian interpretation of probabilities. So there is an empirical scenario in which a rational agent, which could be an automata, must take a decision, and with that aim he must define a degree of belief function. Different possible experiments and results are available, and they are organized in an event structure, assumed to be an orthomodular lattice. This could be, of course, generalized, but the more mathematical developments need to be introduced. So if the lattice of events that he is facing is Boolean, then he will obtain Kolmogorov theory. But if they are not, he will obtain more general things like quantum states. So the natural information measures will be Shannon's, or more general ones, according to the algebraic structure. This kind of approach would allow for natural justification for the peculiarities of arising in quantum phenomena from the standpoint of the Bayesian approach. But this is not the only one. This is not the only possibility. But But one of the problems of the Bayesian interpretation of probabilities, or one of the criticisms that will be raised against it, is that it says nothing about the ontology in a deliberate way. So what can we do if we want to go beyond the subjective approach and say something about the nature of the models involved? It is possible to assign concrete properties of the system to these experiments. In the quantum case, the Cohen-Specker theorem poses a serious threat to this attempt. It is not possible to establish a global Boolean valuation to the elements of the lattice of projection operators. As a consequence, it is not possible to consider the quantum systems as a bundle of actual properties. One of the key features that allows for the existence of this theorem is the fact that the orthomodular lattice of projections is not Boolean. But then, the event structures associated to more general models can be non-Boolean in general. So this means that a similar argument must hold for non-Kolmogorovian models. Indeed, when the orthomodular structures underlying the Cohen-Specker construction are studied, it is possible to show a generalization of the Cohen-Specker theorem. This is some of these authors. And for example, in the von Neumann algebras approach, you can look at this paper. So what this is telling us is that if we want to attribute actual properties to probabilistic models which depart from the Kolmogorovian setting, we can have problems like those appearing in quantum theory. So one possibility, of course, is to use hidden variables. That possibility is always at hand. But sometimes hidden variables present some problems, like explicit non-locality and so on. So due to the existence of these results, an interpretation based on bundles of actual properties for generalized probabilistic models is threatened. So how to cope with this fact and at the same time try to find an ontological alternative to Bayesianism? So recent approaches based on bundles of properties, possible properties, could be used for this purpose. See, for example, this work of Da Costa and Lombardi, and it's relatively recent. So there are actually philosophers have developed, and logicians in this case, have developed frameworks for dealing in an ontological way with these problems. So the elements of the projection lattice of empirical propositions are considered as possible properties of a physical system, and the probabilities of actualization are provided by Bohr's rule. So in this approach, the realm of possibility is taken as real. Systems are considered as bundles of possible properties instead of actual ones. So to conclude, in this paper, in this talk, we have studied the connection between the event structures associated to general non-Kolmogorovian models and measures representing states. We reviewed an approach in which states are regarded as functions measuring the degree of belief of a rational agent, and find that the Bayesian interpretation, at least in this sense, is suitable for them, provided that contextual phenomena is accepted as a starting point. This is a strong assumption, of course, it's not like that. Thus, we find that the generalized version of Bayesianism, in some sense, is meaningful in this setting. In order to provide an ontological interpretation, we have also discussed the condition under which these event structures can be related to properties of a system, and inquired on the ontological aspects of such an association. Due to the existence of generalized versions of the Cohen-Specker theorem, we find that for the majority of models, the description of systems of bundles of actual properties will be problematic. Not impossible, I'm not saying impossible, because one always can go and look into hidden variables. There's a lot of work on this, even in this setting. But a quick alternative could be to postulate, as I said, hidden variables. But these hidden variables should be contextual or highly non-local, as the quantum case shows. If it is desired to avoid these features, a different ontology should be looked for. This opens the door to a generalization of previous approaches in which bundles of properties, possible properties, are elementary bricks out of which reality is constructed. Well, thanks, that's all.
Federico. Questions? Go way in the back first.
So just have a quick question on can you hear me?
Yes.
Okay. I just have a quick question on the suggestion of hidden variables as then being highly non-local. Just because whether the non-locality is EPR or not, formal or informal, hidden variables are generally, as I understand, believed to be dynamical deterministic agents to non-locality. So why would, in what sense are they being considered non-local?
In quantum theory, not sure I understand your question, but in quantum
So
theory,
my question is that in quantum theory, EPR experiments can be explained. Say, any non-locality or entanglement can be explained alternatively by looking at hidden variable theory. So it is really a situation where you're having hidden variables as being dynamical agents to explain non-locality. So I don't understand what you are expressing when you say that the hidden variable should be highly non-local. So could you explain?
well, I would put you an example.
Okay.
Consider Bohmian formulation of quantum mechanics. In this formulation, you have hidden variables, which are particle trajectories and so on. So you have a strong realist interpretation of quantum mechanics in the old metaphysical tradition of point particles. But you quickly find that these particles are guided in a local way by a Bohmian potential.
Precisely, and so the explicit insertion of hidden variables is to actually explain non-locality, not to.
Yes, but they explain.
But how are they non-local? They're actually explaining they're replacing the idea of non-local. So hidden variables are supposed to replace the idea of phenomenon non-locality. So why would they then be considered non-local?
I say if you assume local realism, right? Then
If I may, I think that.
I don't understand.
Yeah, I think that what she's saying is the problem is that when you construct a hidden variable model, you need to a realistic hidden variable model. You need to put interactions between the particles that are non-local, that are superluminal. That's what he means when he's talking about those being non-local.
So it is right. So then he's actually categorizing the hidden variables as those which actually create the interaction between two highly non-local entities. So therefore, there's a confusion in the terminology then, because the hidden variables themselves are not non-local, but the hidden variables explain the effect of non-locality or replace the idea of non-locality by actually being those hidden variables that are utilized as interaction between particles in a deterministic way.
Okay, I think I get your point. Yes,
Okay,
maybe I
so
should
you
refine the
know-
way in which I explain this.
Okay,
Yes,
okay,
you're right.
thank you.
So this last part about possible properties is really tantalizing. Could you say something about the transition from the possible to the actual, to say is governed by going through?
Oh, yes. Essentially, you have to accept that possibility is an existent potentiality or possibility is something real.
Yeah.
And then you have a rule of actualization, like in, for example, model interpretations of quantum mechanics. This variant is like a model one. The one that I mentioned in this article, but there are other approaches based on. This is not the only one. I just put one because I wanted to show that it is possible. It's a possible line of research.
Okay.
Yes, but
First of all, von Neumann, in my understanding, did two orthomodular lattices, modular lattices, basically looking at forms of projective geometry to new versions of quantum mechanics. If we go to the more general case of orthomodular lattices, in general, they don't have probability functions. and we sum that probability.
Yes.
And the probability, and they describe rather different types of situations that many of them would have nothing to do with quantum mechanics.
Yes.
So that's a much more general form, and it seems you're bouncing back and forth. One looking at something very general, which cannot be interpreted back into quantum mechanics, perhaps hopefully in psychology in some place, and then other ones that can. Is that correct?
No, I see your point. I mean, these kind of models, even the one, if I say measures over orthomodular lattices, it is too big. Orthomodular lattice is a big category, as the one of convex sets.
Right.
And then, of course, in this big family, there will be toy models and non-realistic physical theories. And of course, there are even orthomodular lattices for which no measure in the von Neumann sense can be constructed. So these models must be disregarded. But what is interesting is that some physical theories, suppose that you go into algebraic relativistic quantum field theory. I don't know if you heard about that.
No.
Yes?
No.
So there are attempts to find a very formal, solid, to develop a quantum field theory in a mathematically solid ground. There are many attempts. For example, local quantum physics, the book of Hack, is one of these attempts. It has its own problems, but it's a large story. But in these cases, the algebras associated to particular regions, for example, diamond regions of space-time, are type 3 factors, which are von Neumann algebras, which are not isomorphic to those of the typical standard quantum mechanics, you see? So these factors have orthomodular lattices associated, and these are models of interest. So you have indeed examples of physical theories which tell you you should depart from quantum and classical, standard quantum. So this framework, so if I ask you, which will be the lattice structure of associated to a quantum theory of gravity, to the real one? We don't know. You don't know because people look at string theory and so on. And then if you are looking for new theories or new models of quantum-like theories, as von Neumann was looking for, then you need a general framework in which you can look. It's similar to that of differential geometry, which is the geometry of space-time. So I look at differential geometry. There are many kinds of differential varieties, right? So this is you get families and you try to. The same applies for convex sets. For example, one of the most important problems nowadays, I mean, at least there's a big community in physics trying to do this, is if I take the non-signal polytope, which are the actions, the informational actions, which tell me how to separate quantum mechanics from all other possibilities, including toy models and so on. So, I don't know if I'm answering your question.
Yeah, we should cut it here because we have to move on.
Okay.
So let's thank the speaker again, Federico. Good job.
Gary.
Do something really similar.
Huh?
Except I was
Mark is going to use this.
He's going to use this.
rather than-
You're going to use this computer, right?
Yes,
And you have the. Did we copy this already?
Yes.
Did we copy your? I think we.
I would take a really good hand.
was the wrong one. Here it is. Yes.
Let's welcome our next speaker, Mark Burgin. You gonna use this? Or?
Make sure that it's on.
So the problem is, what are negative probabilities? How to understand them? And this problem was from the very beginning, when physicists encountered or actually found that they used negative probability. So let's look a little bit at the history of negative probabilities in physics. And the first was Hermann Weyl, in whose paper published 1927 first appeared negative probability. But neither Weyl nor any other physicist observed this, understood that those functions, those probabilistic distributions that were used in that paper were able to take negative values. Then, explicitly, when physicists saw this, negative probabilities emerged in physics in works of Dirac and Heisenberg within the context of quantum theory. However, both physicists missed its significance and possibility to take negative values. So they also didn't solve this possibility that their probability distributions were able to take negative values. And it was discovered only later that they did this even before Wigner in 1932. And Wigner came to conclusion that that quantum corrections often lead to negative probability. So he was the first to understand that negative probabilities came to physics. And later historians found that they actually came in works of Dirac and Heisenberg, and even much later, the paper of Weyl was discovered, in which also probabilistic distribution took a negative value. And here it's explained how Wigner came to negative probabilities. I will not repeat this, it's possible to read here. However, Dirac was the first who not only supported Wigner's approach, but also introduced the connected concept of negative energy. And he wrote, negative energies and probabilities should not be considered as nonsense. They are well-defined concepts mathematically, like a negative of money. However, at that time, it was not completely true. Because what did it mean that they are well-defined concepts mathematically? They were defined as negative numbers, as some functions that take negative numbers, but they were not defined mathematically as probabilities. And for a long time, and even now, researchers called these probabilities quasi-probabilities, assuming that they are not really well defined mathematically as probabilities, not simply as some function. And Dirac also suggested that negative energy solutions and negative probabilities would jointly lead to the cancellation of divergence in quantum electrodynamics. However, he was not able to achieve this goal in his theory. And it's still a big problem, infinity that appears in physical theories. The next great physicist who wrote about negative probabilities was Richard Feynman. In his keynote talk on simulating physics with computers, he said, the only difference between a probabilistic classical world and the equations of quantum world is that somehow or other it appears as if the probabilities would have to go negative. Not simply that they can go negative, but they have to go negative. This is the next step in understanding of negative probabilities, from a possibility to necessity. And Feynman, in his famous paper published in 1987, studied negative probability and discussed different examples demonstrating how negative probabilities naturally exist in physics and beyond. However, the importance of Wigner's construction for foundational problems was not recognized until much later, when Wigner's quasi-probability distribution, little by little, has become very popular in physics, finding applications to many different physical problems, including quantum optics, statistical mechanics, hydrodynamics, nuclear theory, and quantum field theory. Moreover, it was demonstrated the necessity of negative probabilities, and also it was revealed that negative probabilities are indispensable for describing the realm of antiparticles. So in some sense, they are necessary for representing existence of antiparticles. And we'll see this later when the theory of symmetric inflated probability will be discussed, and axioms of this theory will be demonstrated on this screen. And besides negative probability came to other areas, and for example, Lowe also argued that the use of non-positive probability is both inevitable and natural. So negative probabilities came to economics and finance, to social and behavioral sciences. You can see here known names of those who organized this conference, and to machine learning. At the same time, different researchers also emphasize that interpreting negative probabilities is a difficult problem. And you also see here a reference. It is also interesting that two well-known researchers in 2015 declared that negative probabilities were obviously inconsistent with the frequencies interpretation. And this happened 5 years later after the frequencies interpretation has been published. So what was the difference? Why this happened? And this situation depends or expresses contextuality. So what was the context when Blas and Gurevich declared inconsistency with frequentist interpretation? The context was thinking inside the box. What was the context of building frequentist interpretation? The context was thinking outside the box. So we see how contextuality influences the result. And so in this talk we consider an axiomatic mathematical theory that includes both negative probabilities and probabilities larger than 1. That's why they are called inflated probabilities. And it will be also explained how it is possible to naturally interpret such inflated probability. And it's necessary to mention that both Dirac and Feynman also wrote about necessity of such inflated probabilities. They didn't call them inflated, they called them larger than 1 probability. But they considered that they are also necessary in physics. And it was found that they are also necessary in economics and finance. This was done in my works together with an expert in mathematical finance, Günther Meissner. So let's look at construction and notations of this theory. So usually we consider a set of elementary events. But in contrast to the conventional probability theory, this set consists of 2 parts. There are positive elementary events and negative elementary events. And this is very essential to this theory and to possible interpretation. Because this theory is fundamentally based on such interaction of quantum particles, which is called annihilation. So this theory, in some sense, has very strong ties to the problems of this conference, because this is just quantum interaction. So we have events and we have anti-events. And this theory is symmetric because any event has anti-event, and anti-events of negative events are positive events, anti-events of positive events are negative events. And here is how we formally define annihilations of 2 subsets of elementary events. So, even if we have in X and Y event and its anti-events, they annihilate one another. This is simple physics, what happens in nature. A particle and antiparticle annihilate one another. But it occurs not only in physics, but also in ordinary life of people. For instance, a person has stocks in 2 companies. And if in 2009 the first set of stock gave profit $1,000, while the second set of stock dropped by $1,000, then the combined income was 0. the loss annihilated the project. It's what happens in real life. And this explains what Dirac and Feynman wrote about negative money and what happened in mathematics when negative numbers appeared. It's interesting to know the history of negative numbers. And I will repeat very briefly that negative numbers, as the majority of those who are here know, appeared in ancient India and China millennia ago. But European mathematicians didn't know negative numbers. And negative numbers were brought to Europe through the books written by Arabic mathematicians. They were the bridge between Indian and Chinese mathematics. And what's interesting, when negative numbers came to Europe, at first the majority mathematicians did not want to accept them as numbers. Then, even in the 19th century, several well-known mathematicians and physicists wrote that it's impossible to have such numbers which are called negative, because what can be less than zero? And the same argument was used for negative probabilities. How probability can be less than zero? It's nonsense. The situation was repeated exactly. And, for example, Acacia de Barras found a book published at the beginning of the 20th century with this statement. So, even 100 years ago, there were mathematicians who rejected negative numbers. But for us, it's very ridiculous. So I think that in a while, negative probabilities will become also so natural that researchers will not understand how it was possible before to reject negative probabilities or call them quasi-probabilities, because they are so natural. So the situation was very similar. And really now, negative probabilities are becoming more and more popular. For example, before coming to this conference, I did a search in archive. And even in archive, in 2016, and it's only half of a year, it was published at least 12 papers which used negative probabilities. So more and more researchers use negative probabilities, and not only in physics, in different areas. And we can see this here, an important statement, that when we consider the algebra set of events, F, then events in this set algebra don't contain such pairs, an event and its anti-event, because they annihilate one another. This is like having electron and positron in a very small volume. Then, if we have some event that is the subset of, actually X is the subset of omega, not of omega plus. Then we have a positive part of the event and a negative part of the event. I'm sorry, here is a misprint. X is a subset of omega, not of omega plus. It's a misprint. And if we take some event that is a set of elementary events, and if we take anti-events of all these elementary events, then we get the anti-event of the given event. And elements from F minus are called negative random events or random anti-events. And another interesting example of negative objects, one example is given by antiparticles, another interesting example is given by anti-patterns, which are negative design patterns in the software industry. There is such a concept as negative design patterns. Now, let's look at this theory. So we have here some axioms which define a correspondence between positive and negative events. First axiom defines some order structure, that there is involution of the set of all elementary events, and with the following property. I will not repeat, they are on the screen. If you want, you can write down. If you don't, you want, I hope sometimes it will be published. Then there is algebraic structure of the algebra of positive events, that it is a set algebra. And this is the classical definition of a set algebra that is used in measures theory. Then there is operational structure that shows how annihilation of events and their anti-events acts or impacts this set algebra of random events. And there is also a composition axiom that tells how events are constructed from elementary events and anti-events. That they must not have elements in common. Here are some properties of these constructions. Here, this operation plus in a circle means union with annihilation. If you take two events, not necessarily elementary, and you take their union, then when there is an event and the corresponding anti-event, they annihilate one another. And so the result does not contain any of them. So it's a new operation. Then this mapping, this involution alpha is one-to-one mapping so that the number of elementary events and anti-events is the same. And this also shows that this theory is symmetric. So there is domain symmetry that for any positive elementary event is corresponding negative event or anti-event. Then there is element theory that if we take anti-event of anti-event, we come back to the same event. At first, corollary 2 tells us about elementary events, and corollary 3 tells us about any event, and some other properties. Now, we can see that the set algebra of positive events, the properties of the set algebra of positive events are inherited by the set algebra of negative events, and are also inherited by the set algebra of fault events. So this is what did not exist and does not exist in the conventional probability theory. It's something very different, but this is what actually exists in physics. So when we have this physical interpretation, it's very natural property. But they are proved based on those axioms. They are not simply introduced as something very natural, but they are proved. These are theorems in this axiomatic theory. Then we have axioms that define probability function. So these 4 axioms, and there are additional axioms. First, there is upper normalization. Because this is inflated theory, probability of all positive events is not necessarily 1. It may be larger than 1. But in this theory, we take that this probability is bounded. For example, probability of all elementary events cannot be larger than, say, 5, 10. And for positive random events, probability cannot be less than 0. So we can see that, and we'll see this later, that in some sense, if we restrict all events only by positive events, we actually will come to the conventional probability theory and to the conventional Kolmogorov axiom. It's also a theorem of this theory that Kolmogorov theory is a sub-theory of this theory. When we don't consider negative events. Without negative events, it becomes exactly the classical probability theory. And you can see here the classical axiom of finite additivity. Besides, there is this axiom of adequacy that if you take 2 events which are equivalent, that is, one event has events and their anti-events, In another, for example, in another, all these pairs annihilate one another. Then the probability is the same. Naturally, this triad omega f and p is called the symmetric inflated probability space. Then the number p of a is the probability of the event A. And important theorem is that these axioms, or the system of axioms, is consistent. It is important to prove this theorem for any new axiomatic system, because it's possible to invent such axioms that actually define inconsistent system, and then it would be possible to derive any good statements in this theory. So in this theory, these axioms are consistent, and then we get some properties of this inflated, symmetric inflated probability. So, for example, probability of union and union with annihilation, probabilities are the same. Probability of random event is equal to the negative probability of its anti-event. Then probability of the negative, full negative full negative elementary events, the set of full negative elementary events, gives the lower bound for negative probability. It's a negative number. Then what we have, that for example, in this theory, probability of the set of all elementary events is equal to 0. Very unusual property. In the conventional theory, it's equal to 1. In this theory, it's equal to 0. Then about interpretation. So these axioms look very unusual, and it's really not so simple to find a natural interpretation. And because physicists are mostly interested in the frequencies interpretation or frequency interpretation, so here we build frequency interpretation for symmetric inflated probability. That is for probabilities that can be negative and that can be larger than 1. So here we take both, we eliminate both restrictions. Before, as it was mentioned, similar interpretation was given only for such probabilities that were able to take both negative and positive values, but they were less than 1 and larger than negative 1. Here they can be larger than 1 and less than negative 1. And here we define frequency in a different way. We define frequency, we take the number of positive events in N capital trials, and it's N small, and the number of negative events. And then the frequency is defined, the difference between these frequencies. So it's essentially different from the conventional approach. And then we define symmetric inflated frequency probability equal to the limit of such frequency. And we assume that for random events, or quasi-random events, or then quasi-random events, this limit exists.
Excuse me.
Yes.
This large N is the sum of the small n and the
No.
small n? It's not,
No.
right? What is it?
The large N, or capital N, is the number of experiments, of trials, the number of trials. And in this interpretation and in this theory, it's possible that a trial does not give any event, does not result in any event. And it's also a natural, actually, assumption, because we know that there are many experiments in physics that give no result. And so it's natural. At the same time, in this theory, it's possible that a trial gives. Okay, I'm close to that.
Yeah.
Very close. Yes, thank you. That the trial can give not only one event, but, for example, two equivalent or even equal events. For example, an event to find an electron in some volume of space. Physicists organize an experiment and they find two electrons. So it means that it was not one event of finding an electron, because one event is finding one electron. But in this experiment, two actually equal events happen, finding two electrons. And this is how probabilities may become larger than one. So here is explained what actually is a limit. And here I want to make one very unexpected remark, that actually there is a theory that extends the probability theory, in which not only random sequences of events have probability, but in which any sequence of events have probability. This theory is called theory of hyperprobability. But it's another story and another. So let's look at examples. The first example was actually discussed before. It's about stocks of two companies, and one gave profit $1,000, another dropped by $1,000, and combined income is zero. So the loss annihilated the profit. Now second, Bill finds $20 and loses $10. So as a result, the amount of this person's money has increased by $10, not by 12. So the loss once more annihilated, in this case, a part of the difference. So we may take as elementary event finding $1. So this, or losing a negative event, losing $1. So 20 positive events, then it came 10 negative events, which neglected part of positive events, and what is left is 10 positive events. And that's why in that general interpretation we consider differences of frequency. Yes. Okay, I don't have much time, so here is one more example. I don't have time to read it aloud. You can read it here, or you can discuss this after the lecture about probability of printing some word with a misprint. Then another interesting example of probability, that, for example, a person goes to casino and wants to know what is the probability of winning $100. And mathematician calculates and tells to the third person that the probability is minus 0.5. What is the meaning? That actually this is the probability, that the probability 0.5 is that Casey will lose $100 instead of winning $100. And this is different. If you take that the probability is 0 of winning $100, it does not give us, it does not make a difference between simply not winning anything and losing something. When we have negative probability, we can make a difference. Like, for example, with using negative numbers for money. Yes. Okay, here is one example. The last example is how we can have inflated probabilities, or probabilities larger than 1. So I will not read this conclusion. It's natural. The last is the symmetric inflated probability, essentially employs ideas and structures from theoretical physics in general and quantum physics in particular. So thank you. And any questions?
In your example of the casino where Kathy has a negative probability of losing, that
No, negative probability of winning.
of winning, then the house has a positive probability of winning.
Right.
So whenever there's a negative, if I'm hearing you right, whenever there's a negative probability, does there also have to be a positive probability? It's a relationship, right?
Right. That's why this is called symmetric probability.
So can you have a positive probability without a negative probability?
No, in this theory, you have one symmetric picture of the world. There are other formalizations that are not symmetric. But in this theory, you see, it's possible to build not a single one probability theory that extends the classical probability theory and includes negative probability. It's not, there are different. And in particular, I will two different extensions. So in this case, you're right. This theory is symmetric. Always, when we have negative probability, we have positive probability, and vice versa.
Okay, we're going to hold off questions. We're running late, so we should save it for the coffee break. I think. So we are over time. So.
Yeah, I'm sorry, but I'm ready to answer.
Yeah, we have a coffee break coming. So.
Thank you.
Thank you, Mark.